Modeling electrical systems is an important skill for mechanical engineers, electrical engineers, biomedical engineers. No matter what systems you work on, eventually some of them will be automated, especially when we talk about control. So learning how to deal with electric circuits, basics of electric circuits, is very important. It boils down to being comfortable to rearrange equations in order to solve for the variables that are of interest. And in order to get the equations that you're going to manipulate, you're going to use two Kirchhoff laws. The current Kirchhoff law says that if you pick a node in a circuit, that the amount of current flowing in and the amount of current flowing out has to be the same. So in this case, the three currents on the left must sum to be the same as the two currents on the right. And so current is really the amount of charge that is flowing through the circuit. And so it's a conservation law that we're observing here. In the second Kirchhoff law of voltage, we take the sum around any loop, any closed path in a circuit, and that the sum of those voltages must be zero. And so there could be many circuits or many cycles within the circuit. And so you can pick any of them, and they will be somewhat redundant if you take all of them. So for example, we can take going up through V4 is a positive V4. Going down across V1 is a negative V1. Going down across V2 is a negative V2. Going down across V3, we lose V3. And so this means that V4 minus V1 minus V2 minus V3 must be equal to 0. Or if you go the other direction, you can say minus V4 plus V3 plus V2 plus V1 has to be equal to 0. Similarly, we could talk about going around the larger circuit, which involves V1, V5, V3, and V4. And then we can also go across V2 and V5, this circuit right here. And the interesting thing about that one is this is a parallel circuit, and you should already remember that the voltages across a parallel circuit are the same. And so this is what's really being said by the Kirchhoff voltage law. One of the best ways to think of and interpret current and voltage is to think about water. And so the conservation law of current corresponds to thinking about the confluence of rivers, where streams come together and then branch out again, and the amount of water that's being passed through must remain the same. So the amount of water coming in along these three branches has to go somewhere, and so it has to go along these two branches. The voltage represents a force that the water flows with. And so you can think about that as the energy given by how far in elevation it's coming down. So the kind of the potential energy of this water. And so each element, for example, a resistor, represents a drop in that voltage as it goes down. And the pump here would represent, for example, a voltage source. The last pieces of information that you'll need in order to write differential equations for simple electric circuits are the fundamental relationships between voltage and current for each of the fundamental circuit elements. So in what we'll consider in this class, we'll talk about resistors, capacitors, and inductors. Resistors are a static, use a static model, a static relationship between voltage and current. And so if a circuit is entirely made out of resistors, then there is no differential equation element. A capacitor, that's simply just because there's no change in either of those states with time. A capacitor is an element that has two parallel plates that build up charge as current is put into it. So you can see that based on this differential equation, where I is equal to C dV dt, if I were to write an equation for the voltage, this would actually be the integral of the current. And so you can see this is explicitly saying that the voltage is the accumulation of the charge that's delivered by the current I. And so this describes the time change in the value of the voltage based on how much current is coming into it. An inductor is an element that has a bunch of coils. And so if you remember your physics, there's a magnetic field that's created by putting current through a set of loops like that. That's actually how an electromagnet works. And so what happens is there's a magnetic field that's induced in that, and the magnetic field stabilizes the current that's flowing through. And so it resists the changes in current, and that's what's kind of described by its differential equation here, which simply says that once it reaches a point where the current is not changing, so if the current is steady through the inductor, then there's actually zero voltage loss through, because the change in current would be zero, which means that the voltage across this inductor would also be zero. There are also two types of sources. There is an ideal voltage source, in which case it provides a fixed voltage, but with any amount of current, and that current that's drawn from the voltage source is just dependent on what the circuit requires. On the other side, there's an ideal current source, which means that it has a fixed current flow of charge that's going through it, but a variable amount of voltage. So these are all the elements that you need in order to compose differential equations for circuits. And what it boils down to is essentially writing down all of these things, substituting, and trying to figure out a reasonable set of substitutions in order to yield equations that give you information about the parts of the circuit that you're interested in. Perfecting that is a matter of practice.